everyone. So this is the lecture for vibrations and waves. Just to clarify, in your textbook, that will be chapter, let me see, 12 or 13. I got to double check here because that's different edition. So it correlates with the book I have here with the slides I'm using. This lecture is gonna be all about oscillations, the theory, okay, of oscillations, a little bit of simple pendulum, some of the equations, some of the logic behind it, a little bit about damped oscillations, and then on the next video, I'm gonna do some of the wave assign sample problems, okay? You have to be a little bit more careful with this topic because here you are dealing with springs, okay? You have used springs in the past in physics 1 when you use the Hooke's law, negative kx, where k is the constant of the spring and x is the displacement from the point of equilibrium, okay? K is in newtons per meter, x can be measured in centimeters, but you always have to write x in meters, okay? The negative kx is basically the restoring force, right? F equals to negative kx, and that's why you can have a periodic motion. So that's the main idea of this lecture, right? We're gonna be looking at periodic motions, simple harmonic motion, where you have a spring mass system and no friction. And then we're going to analyze what happens if you add some sort of damping in between, okay? The major application of oscillations is your simple pendulum, which you may have done an experiment with, where you can get the period and the value of gravity. And basically, the way we characterize these motions is by the period. The period is the inverse of frequency. Frequency is the number of oscillations per time. So let's say you have a simple pendulum. If it goes back and forth, that's one oscillation. So the period of one oscillation is the time to go back and forth. Okay? Now, we normally do it for more than one oscillation. So if you are taking 10 oscillations and you take the time for 10 oscillations, the period is the time for 10 oscillations divided by 10. Okay? The period is the time for one oscillation. Okay, that's why frequency is defined as the inverse of the period, or one cycle, as this is here. So, as I said, if you have a spring, you're gonna have the Hooke's law acting on it, and if you move the mass to the right, then because of the restoring force, you're gonna have the block moving back and forth. So you have a periodic motion, right? The mass starts from rest, you release it, and then it goes back, stops, and then goes forward, stops. So there is a point of equilibrium right on the middle, here. That's where the mass acquires the maximum velocity, to the left or to the right. The amplitude is basically on the extremes. So if you elongate the spring and you let it go, that's the amplitude. The block will never go beyond that point because of conservation of energy. So we can use sine functions or cosine functions to analyze and quantify this type of motion. A is the amplitude, V, if you take the magnitude as the speed, and then you can have the displacement written like that, right? Or model with a sine function, okay? Where the top is the amplitude, and then you go from positive A to negative A, positive A to negative A. You can use sine, or if you start from the top, you do this, that's a cosine function, which is why you have here this equation. Remember that between sine and cosine, there is a period of, there is a phase of 90 degrees. So this function, I can change it to A sine 2 pi over t times or plus pi over 2, right? That would be basically your sine function there. Now, what's 2 pi over t? That 2 pi over capital T is W. That W is the angular frequency, okay? Which is why in some textbooks, you're going to find the following. You're going to do it like this. X equals to A cosine, let's use cosine still, of omega t or WT. It's lowercase t there. W is 2 pi over the period. Capital T is a period. Which, by the way, is also 2 pi f, where f is the frequency in hertz. So this is measured in hertz. This is measured in seconds. This is measured in radians per second. Radians per second. This is measured in seconds because that's unit of time. And this is measured in 1/seconds, which is basically hertz. Very important, guys, the units, okay? That's part of your metric system there. Okay? So we can model the simple harmonic motion in a mass spring system using that. Let's erase this. So there you are. From A to negative A, an object in simple harmonic motion has the same motion as one component of an object in, yeah. So we can normally use circular motion to model this, all right? Because it's sort of the same idea. You have a mass going back in one period, right? The period of the motion in the circular motion, as you remember, is basically the time for one revolution. So one cycle is basically one revolution. Okay, so you will see in some textbooks or even here that you can use circular motion to do the analogy for simple harmonic motion. So period was in circular motion, angular frequency, all of those parameters were introduced in circular motion. All right. So the position versus time can be written like that. And here are all the parameters I was mentioning. Okay, so instead of theta, which we use in circular motion, we can use WT. Okay, so if you think about it, that's your equation for circular motion, right? For non-accelerated, for a constant rate circular motion, the angle theta is equal to WT. That's a relationship that you guys should know from Physics 1. Now, a little bit of calculus, since I know some of you guys have taken that. If I take the derivative of the position with respect of time, I get a velocity. Okay, so velocity as a function of time is the first derivative of position with respect of time. Now, I'm not going to ask you to do this in an exam, but if you take the derivative of cosine, you get negative sine. Now, you also do the chain rule, so you do the derivative of what is inside with respect of time, so the W goes out. So you should get something like this, negative AW sine of omega t. The negative is just a direction, by the way. Yeah. And by the way, this AW is the magnitude of that. So WA or AW, that's the maximum. That's the equation for maximum speed. And if I take the derivative of velocity with respect of time, that's the acceleration. dv dt. Okay? You will get negative AW squared cosine. Again, the sine is just, So that's basically, all right. If I clear this, you can find the equations here. All right. W squared A is the maximum acceleration, WA is the maximum speed. Now, if you use the Newton's second law, force equals to mass times acceleration, ma equals to negative kx, that's ma, kx, and you get a nice equation for W in terms of k and m. So you can find the value of the angular frequency if you know the constant of the spring and the mass of the block. You can also find the period. The period of a mass spring system is 2 pi over W. So 2 pi is square root of m divided by k. It's another important equation. Okay, so yeah, a lot of equations in this unit, okay, in this chapter, and you're gonna see how they are used in the problems in the next video. But you know, it's a lot of these equations you can find them from just one original equation if you know the definitions of velocity, acceleration, and Newton's second law in this case. But you can always write them down in a small formula sheet. So here is a model that we use, right? Depending on the period, depending on the amplitude, you can have functions like this, right? The reason this is more elongated than this is because of the period, okay? If you increase the force constant by a factor of 4, you are decreasing the period, you are increasing the frequency though. So that's why you see more of this. More frequency means more waves per time, more cycles per time. That's more frequency. But more frequency means less period. So it takes more time to complete one oscillation, all right? Oh, sorry. More frequency means less time. So you have less time for one oscillation. That's here you have more time for one oscillation because you have less frequency, less frequent, right? Now for the energy of this, you have the mechanical energy, kinetic plus potential, kinetic plus potential. Now we don't have gravity, is a potential elastic given by 1/2 kx squared. How do you get that? By doing the integration of kx dx. All right, you can integrate f dx. That's basically work. All right. And when you integrate that, you get a nice equation for the work done by the force, by the restoring force, which is 1/2 kx squared. All right. So if you use equations for V and X that we had here, you get this equation for the total energy of the system, 1/2 Ka squared. All right. So you have here another equation here now for the energy at all times. All right. So because the energy, the total energy depends only on the amplitude, then it's just a constant. However, the kinetic and potential, they depend on the values of V and X. So that's why they change as a function of time. And that's basically everything that you need to know for the mass spring system. Now, for applications of this, you have simple pendulum, all right, which you're going to see more in the problems. The main thing I want you guys to see in this slide is this equation for period. And then for the physical pendulum, which you can have like a bar and a center of mass. The difference is that for a physical pendulum, you have to take into account the moment of inertia that you did in physics 1 as well. Okay. For damp oscillations, guys, the only thing I want you guys to know is that this happens when there is a dragging force acting on the mass and it's making the oscillations stop. Okay, so you have a situation like this, right? The amplitude is decreasing by a factor of E negative BT over 2M, where B is the dragging coefficient. All right, you need more calculus for this, and I might show you in the problems next video how this works. It's an interesting part of the of oscillations, but we do that more in mechanics. in a proper mechanics course, because you need differential equations to actually solve for the value of the position as a function of time. Okay. Other than that, it's not a very long lecture, guys. What I will do is I will go over problems on the next video, and you will see how some of these equations are used. Again, this is chapter 13. So make sure that you guys are reading your book and the slides, and I will see you guys on the next video. Bye-bye.